people, what's up? Welcome to the first ever episode of the Curiosity Project, where we delve into the minds of interesting people and try to decipher their stories and insights for us to learn from. Today we are speaking to Professor Radhakant Padhi. Dr. Padhi is currently working as a HAL Chair Professor in the Department of Aerospace Engineering and also as an Associate Faculty at the Center of Cyber-Physical Systems, Indian Institute of Science, Bangalore. He has also worked on our national pride, Chandrayan 3. His research interest is on control synthesis algorithms and their applications to challenging problems in aerospace, biomedical, and mechanical engineering fields. We are approaching him with our novice questions on satellites, Chandrayan 3, and space exploration in general. I personally enjoyed today's podcast. And with that, I shall let you dive in.
Lovely. But firstly, thank you so much for joining us today, sir.
Yeah, thank you for coming here on that too on a Sunday. Coming from very far off and all that. Thank you for that.
I'm very glad that you gave us time today. Firstly, before we start talking about the projects in specific, we would like to understand you better. Like, where do you come from? How did you start? And how is your, interest into control systems in specific, or maybe space exploration in specific start? We'd like to hear your story from your end.
From childhood or whatever, so you can always become a little bit fascinated about math and physics. And then when time came for doing career choice, and we had to do a lot of struggle that point of time. So not these many options were available. So we have to have multiple trials and then go into either engineering or medical, which is even there today in that kind of person. So I got selected in an engineering stream for the second attempt, and then I was selected for mechanical stream. So from after completing mechanical, then you think about specialization, where your heart belongs to. So that point of time, around second year of mechanical engineering, I thought I'll do master's PhD. This is the career that I wanted to do. And then during third or fourth year, I was kind of fascinated or passionate about aerospace engineering. I told aerospace is where I can, my heart belongs to probably. So give it a try. So then fortunately aerospace, actually if you see aerospace is 70% mechanical. Mm-hmm. Mechanical aerospace, that's why in US and everywhere you will see mechanical aerospace departments are together. Very rarely they are separate out altogether. So with that in background in mind, I appeared for GATE, and GATE score was fortunately high. Mm-hmm. And I got selected here in IIC. That's how I've done my masters here in aerospace. Then I've done, in the beginning itself there was something called IGMDP program, which Dr. Kalam started for missile program, missile systems. So I got selected there. And after masters, I joined DRDO for a year. And then quickly realized that I need to do PhD early. So thought of returning back to DRDO or ISRO later, but let's do the PhD first. So 1 year later I quit DRDO and went to US for PhD. Did my PhD postdoc both there, about 4.5 years for PhD, 2 more years for postdoc. Then I was searching for options. I was never very serious about staying back in US. I was just exploring options out here. Got a bunch of options, IIT Kanpur, IIT Bombay, Madras, all sort of thing. But this is where my heart was. So I also got selected here, so I thought I'll come and join. That's the story. So I joined here in 2003 December, and since almost 20 years, so 2 decades passed as a faculty here.
Lovely. So it's been like 20 years of journey, right? Okay. Speaking of your childhood days or your student days, what was that one interesting project that you have worked on and you felt like, oh my God, this was the best student project that I could have ever done?
Well, in our time, I don't think the things have changed. Now people BTech level, they talk about so many projects, internship, doing all over the place and things like that. In our time, we are talking about 30 years back, 92, 91, like that. So that is a time where not too many options were available. We were called something called industrial training that our college used to give. This is a state government college, by the way, in the state of Odisha. So you can select a bunch of places to go and see what's going on. Not that too much internship, that much exposure was not there, internet was not there. Only whatever your parents or brother or something can talk about. That not too much of internet flow was, information flow was not there simply. In fact, while I was going to US, that point of time also I was not burdened with so much of information. Okay. So information flow happened only in 2000 onwards basically, when the internet was coming, and then lot of information happened basically. There was no YouTube, there was nothing to see in the internet, nothing. So only by talking to friends, talking to seniors, talking to faculty, like that whatever you have actually that way. So we grew up in that sense. So when you go there, whatever industrial exposure we got. In fact, the very first industrial exposure I selected ISRO, by the way. I don't know, many people don't know about it.
Okay.
So second year of VTech, I was selected, all the list will come, the training and placement center, you have to tick one. So people used to select which is nearby and which I can do it home quickly and things like that. But I thought this was my first train journey in life, which was like 44 hours. Okay, from one and east part of the country to west part of the country. I went to something called SAC Ahmedabad, Space Application Center Ahmedabad, which even now is a very pioneering center of ISRO, which provides a lot of sensors and payloads to the satellites basically. But because I was from mechanical department, they put me on something like manufacturing department. So the CNC machines were coming new and all that fun time. So all entire month went for looking at how the CNC machine operates and all that. So it was not very exciting that way. But then second year, when it comes to third year, I selected another faraway place, which is actually in the state of Karnataka, where you are sitting. Okay. So this is the this Dharwad and all that. So that point, right, this Mysore Kirloskar is there. So I selected that one. So to come and see the Mysore Kirloskar plant, and then that was another 1 month of just exposure of what's going on. We are not given any hands-on training. We are not given on any project per se. And BTech college teachers are not really passionate about research, so research exposure was also very less. Basically.
So what was the exposure in terms of research field itself, so when you were growing up? Because when we consider research nowadays, I'm not sure how many folks are really interested into research, and I do not know as to how far people were interested back then. Like, was research considered as a field of study? Like, how do you go about your career in research?
Well, I always tell my students particularly, research is nothing more than common sense basically. Just apply systematically. Okay? So you think about some problem and think about a little bit of rebel mind, in the sense, okay, not really in fighting or something like that, but then when you see something, do not accept things as it is. Always think about how to improve it, let's say. Okay? You think about something operating, don't get happy about it. So then how to improve. That's how all these cell phones came. Like earlier started with only talking, then a little bit fast, little bit data, then fast data, SMS. Then there was some time people were moving with pagers. Now we talk about pagers together, now music together, camera together, just one device and a pocket in a computer sense. I mean, all your files are in cloud, everything there, right? So if you are happy at that point of time, just by talking, remember the phone itself was a scarcity. I still remember before going to US, I was still going to booth and all that. There was no cell phone. Okay? Now cell phone, the moment it comes, you are happy, then life stops there. So you always think about how to do more, better things like that. So research is not really very painful. Research is actually enjoyable in that sense. And end of the day, you come up with something that nobody in the world has ever done it before. And not just the current generation. Remember, it is not literature is something that you can recreate the same thing again and again, tell in a different story. Like different angle, right? That's why you see the same movies being told in a different way, with time. But research, we do not have that luxury. You have to really go for the history, whatever people have discovered or invented, that's the fact. So given that fact, you want to take it little more actually, right, that way. So your constraint becomes much higher basically there. But having said that, the process, the moment you get something out of that, that means not only the current generation, but nobody before the generation also has done that. You are the first time. So looking at that and getting your name published in some IP, in the sense of papers or publication, that's a very different thrill that you get.
That is true.
And then that itself should be a drive force for you to do next one like that. So before you realize, it becomes a habit for you. And I can again say, research is not really something to be worried about or afraid about or anything like that. It just comes naturally. You think something systematically, something is happening, why it is happening, what can be done to do it better. And especially engineering research, we always talk about doing products basically, doing things better, whatever. It has to be, the science has to be realized for people's benefit. That way. And someday you will dream that, okay, your product will eventually be useful for some big things, like some product or somewhere that people's life can change, or maybe country's mission you can get involved in. So these are some of the bigger things that you think about impact of research. Okay, so those things will drive you further basically.
Now, speaking of the country's mission, it gives me a very good segue to get started with Chandrayan 3. So before we get started with Chandrayan 3, I know you were a part of an investigation team from Chandrayan 2 perspective as well. Is it possible for you to give us insights on what actually went wrong with Chandrayan 2?
Now it is all public domain. Even ISRO chairman himself has told, so I don't mind talking about it, whatever best I know basically. Mm-hmm. So this was about when the mission really didn't work. Okay, there was immediately, almost the next day, there was a committee to figure it out what will happen. And ISRO never called it as a failure analysis committee. They always want to call it as a performance analysis committee. So this is also a good thing to say basically, right? Either failure or success. It is not really complete failure, by the way, because even the satellite actually helped us doing the Chandrayan 3, right? So that way. So it was not really failure in that sense. Something went bad where country was looking for. But because the satellite was there, it gave a very huge impact in the Chandrayan 3 mission later, basically. So we cannot call that Chandrayan 2 is a complete failure in that sense. Now coming back to that, okay, there was a problem in landing part itself. We all know that. And landing, what happens is actually you are talking about an orbital velocity, right? I mean, you are moving in the orbital velocity of the moon, which is not really very small, because even though moon gravity is 1/6 of Earth, still the velocity at which you want to go around moon is not really very small. Okay? From that value, you almost got to get it to the zero value, and that too with the vertical position and all that. So it's a little bit complicated mission. So you have to have so many sensor uncertainty. Remember, you are not flying with it; it's autonomous vehicle. Sensors have to operate well, and you cannot see and drive. That means the data has to come back to Earth, and then you take a decision. That time is not there. So you have got time latency and all that. It has to be autonomous mission. So in that situation, things went roughly well, but there were a couple of problems. Of course, we noticed it later after a lot of debate, discussion, brainstorming, or whatever you can say. So what really happened there is there are a couple of things, and of course, all these aerospace missions will have fail-back options, basically, right? Unless a series of things fail, normally the mission itself will not fail. In fact, all aircraft accidents are also like that. There are so many things has to happen together for an aircraft accident. Okay, so before see, that's why the aircraft accidents are very, very less, right? And the probability of you being killed in an aircraft accident is about 1 in 11 million, 1 by 11 million. That's the probability that we enter into an aircraft actually, right? So that's that much reliability. But remember, that's a passenger aircraft. So there are so many things has to be taken into account. Now, even in any aerospace missions, we always talk about what if something doesn't operate, right? So there will be failback options for that actually. That failback options were made much more better in Chandrayan 3. Now coming back to Chandrayan 2, what really happened is, there was a little bit of thrust mismatch in the segment 1. There is something called phase 1, phase 2, phase 3, phase 4 like that. People all know about it right now. So phase 1 is the one which operates more or less blindly, I will say. Not blindly in the sense whatever your information you have in the orbit, from there you start your braking basically. So that braking, it was done reasonably well, but then there was a little bit of overperformance. In other words, if you demand some X amount of thrust, the thrust given actually realized by the engine was about 1 or 2% higher basically. So if it is 1 or 2% higher, remember this, the thrust is actually opposite to the velocity, right? Velocity is this way and thrust is that way. So you are braking little higher, that means your velocity is reducing basically, right? So it is reducing for a longer time, that too, because the time taken is about 10 minutes actually that way. So it reduces small amount of discrepancy, but then keep on reducing. Reducing means what? Whatever you wanted, compared to that, it is reducing little more basically. So it reduced to a point after that segment got over. Then the computer thought that, well, your landing site is somewhere there, I cannot go. So I have to really add thrust. Remember, this is now thrust is opposite to the velocity, right? Velocity is here and thrust is here. Now, unless the thrust is going like that, you cannot add velocity. Okay. So the computer has to kind of rotate the vehicle, because remember, these vehicles are not, they are strapped down engines basically, right? So engines are not really flexible. The nozzles do not deflate compared to the vehicle. Nozzles are very fixed. So if you really want thrust from here to here, the entire vehicle has to move basically. So that is one thing that has to be done. And then there was second problem. That is when the computer realized that I have to add velocity, thrust has to be roughly to the velocity direction, not opposite to that. So when it really wanted to do that, then it has to do quickly. But remember, there was another problem. So because of the legacy of ISRO, the satellite part of it and all that, they didn't want to take too fast rotation. Too fast rotation is its own problem as well. So, there are liquid engines there, liquid slosh effects are there, and also like a pot of water or something, right? So when you put on quickly, then the water inside has slosh actually, right? So that will lead to vehicle oscillation and all that. So to kind of limit all that, they put a very conservative number of 10 degree per second. So the vehicle actually supposed to, like the thrust direction was like that, that means the vehicle orientation is like that. It has to go like that quickly, but this much a quick way is not allowed actually, right? Because the software did not allow it. So it has to do a little bit and recompute, a little bit and recompute. That means when it was going like that and you are not going there, the next time you compute it will be like this, little more. Next time you compute it like this, little more. So it actually took a complete 360 degree turn.
So there was a delay in the operation.
The vehicle itself got a 360 degree turn, one round actually, basically. And doing this, it landed up in a position where the second phase or third phase is supposed to start. And that initial condition for which it was not really designed for. So the next phase was not designed for that kind of initial condition after it takes a turn. So the vehicle, we call that is something like capturability ball, capturability basket. So within the capturability basket, in the sense, okay, physically there is a capturability basket of XYZ, but also there is associated velocity vector. So that means, this x dot, y dot, z dot like that. So within that 6 balls, XYZ and the corresponding rates, If they are within some hyperbole and all that, the 6-dimensional ball, then your guidance is ready to take you there. But after doing all this malfunction and all that, that was not ready actually. So from there onwards, it was a disaster actually. So it could not guide it properly. That's how it is. So the very critical phase of getting vertical and going slow down and all that segment itself was not seen actually.
Got it. So how much time did it take for you to go through this entire performance analysis
We went
phase?
to a big committee. It's not me only. I was it was largely ISRO committee. And there were several other people of their own retired control system engineers and their guidance system people and their engine development people. The entire bunch of ISRO people there. Only 2 academic people were invited. One was from IIT Madras. The second was me basically. So this is only 2 academic people. But we went through quite a bit rigorous exercise for about 8 to 10 days. And morning 9 to almost evening 9 actually. So what if you can remember, all that you are playing around with just a telemetry data. Before the vehicle was lost, whatever data it has sent it back, that's the data you have. You do not have the vehicle, you cannot go there, you cannot see the vehicle basically, right? Unless aircraft there is a crash. So you can go to the crash site and figure it out, the black box, whatever it is, right? Those things are simply not there here. So whatever data is there, you have to play it around and tell, okay, what has actually led to that situation? See, right now we are talking because we understood that basically, right? But to understand that, you have to play it backwards to the data basically. So that itself is a lot of difficulty. So what if this would have happened? What if that would have happened? What if this would have not happened? Okay, all these scenarios you do. So not only we sat down for almost like 7-8 o'clock in the evening, but then some tasks were given to the engineers to figure it out what will happen. And they were actually, heads up to them, they were actually doing that in the night and showing the next day. So that's the rigorous exercise that ISRO goes through basically. And then the reasons were known. The reason were kind of about 10 days later we could know the reasons, but then you have to rectify. So in the rectification process, it went through again quite a bit of exercise. So that is how Chandrayan 3 was far superior than Chandrayan 2.
And with Chandrayan 3, everything that was going wrong with Chandrayan 2 was definitely rectified, right? And it's a matter of national pride right now. And but with respect to what exactly was expected out of Chandrayan 3, what did the team expect for Chandrayan 3 to do as a mission?
Chandrayan 3 the Chandrayan 3 like any other lunar mission, first of all. So even Chandrayan 2 also, it was a little bit adventure thing in the sense nobody has ever gone close to South Pole, right? I mean that's a fact actually. So anywhere that you want to mine or kind of explore, you should rather go to a place where somebody has not gone. So you may actually get something which people have not seen before. That's the whole idea basically, right? And also remember, South Pole is a dangerous area in general because it actually, when the asteroids go through, they actually hit the South Pole. Okay, so see all our, there is something called asteroid belt between Mars and Jupiter. So these guys sometimes escape and then they travel through the solar gravity basically, the sun gravity. When they go through that solar centric gravitational field, sometimes these planets or moons or something, they come on the way. And that is how our dinosaurs got lost and all at that point of time. So the big asteroids and all, it came, and we have got a very beautiful planet, blue planet we call. There is a very big Earth atmosphere. When these guys come, even now they come repeatedly by the way. So when they come through the atmosphere is something called entry conditions, and then entry conditions are harsh. They generate a lot of heat. So they first fragment out a lot of pressure and then force and all that, aerodynamic force and all that. That will fragment out, then burn out, and we are safe. But that luxury is not there in the moon. Moon doesn't have atmosphere. So these people go in orbital velocity and they just bang it actually. That is why you see a lot of craters there. So South Pole of the moon has a lot of craters basically. So when you have a lot of craters like that, finding out a good place to land itself is a challenge. Okay, so but when you have a crater, remember that means something inside the moon is visible, little bit inside at least, right? So that's why a lot of countries are actually going inside the crater also. But we didn't want to go there in the very first sight actually, right? We want to go around the area and then see out what is come out actually. So that was one of the missions, and then of course Chandrayan 3 had several sensors by the way. So you want to study this unlike Earth soil, the moon soil is expected to have some electrostatic charge actually. Okay, so that was you have to study how much is there, what is there like that. Then because there is no water there, of course on the soil, there is water but not on the soil basically, right? So not the soil is dry normally. So how your things will move, what is that content or chemical composition basically, right? What is that moon contains basically? Whether it contains some rare earth element or something, then you can next mission you can go there and grab something and come back. In fact that is Chandrayan 4 is planned for that only. That's called sample return mission basically. But having said that, there are a whole lot of sensors that went through to figure it out a variety of things, including let's say what is the effect of like outer space in the night hours basically, right? Something like that. Okay, right? What is the radiation effect that comes from the Earth Remember, we see moon because the sunlight is reflected from the moon and falls. So you also, when you go to moon, the sunlight is also falls on the earth and gets reflected back. So you want to capture that and see what is the composition there is. So there are many things. I mean, I forgot all that sensors reach and all. That's not our domain typically. But then bunch of data, whole bunch of data would have come, and that is accessible to public. So anybody can do research on that. Especially the physics professors, if you want to ask, they will tell more on that.
Based on this. And from a control system standpoint, that's where you worked, right? So what are the different sections that go into study? So specifically with respect to space exploration, if I'm thinking about control systems, what are the surface level things that I would actually have to touch upon, like the major topics?
Well, like any system, space is of course a critical system. Okay? It is a little harsh system because you are, see, until aero probably you can think about a pilot. Okay? There are also pilotless vehicles, UAVs and all that we talk about, missiles are there, all sort of things. But the moment you go to space, more or less it has to be unmanned, right? Unless you talk about the space station, for example, couple of people go there, stay and come back, or some space exploration, space tourism, very limited things. The actual benefit of space is all unmanned, all satellites are unmanned, right? That way. So this has to be more or less autonomous missions, okay, in some sense. Sometimes they are guided from the Earth also, basically that way. But in general, in all aerospace missions or in any particular control system, whatever, first of all, you know this, what you call system state. What is the state of the system? What is the, for example, chemical plant you are doing, let's say, you want to know what's the temperature of the system right now. Wherever the chemical system is happening, chemical reaction is happening, what's the temperature? That's a very critical part to further accelerate or decelerate the chemical reaction, basically, right? So every time there will be a temperature sensor, and temperature sensors are easy to see, basically. Then you want to put a pressure sensor, basically. Let's say what you want, you can see the pressure, what's going on there. Then you see suppose there is something like a reaction, you expect some product out of it, you want to sense that, how much it has come out and all that. So these are called states of the system. So essentially in any vehicle also, any aerospace vehicle, whatever it is, first thing that comes to mind is something called navigation. So navigation in the sense you want to know where you are in some frame, I mean some relative frame, whatever it is, right? You want to put, you are looking from here, then from this frame, you could put a frame here and then figure it out where that fellow is, where the satellite is. So the first thing is navigation, and navigation contains 2-3 components. It's just not the position. Position obviously we want to know accurately as much as possible. But along with that, you want to know where that fellow is going. It is not hanging, right? Most of the space mission, aero missions, there is not a stationary thing. So unless there is a helicopter hovering or some very limited sense, it will be just there. But most of the things are on motion actually, right? So you like to see the velocity and the moment you talk velocity, it's a velocity vector. That means which direction and how much it is going, basically. Okay. Then you talk about several other things, basically. So for example, see that will more or less give you the good idea, position and velocity, right? In fact, for any orbit, there is a theory for that. Any satellite or whatever in an orbit, at any point of time, any point of the space, if you know only position and velocity correctly, then the entire orbit is determined. That means any other time you can tell where the satellite is. Okay? So those things are supposed, position and velocity is very much critical information that we are after, basically, right? Then there is a little bit of how accurately you do, what are sensors you do. Like, so there are sensor related problems actually. We call that inertial navigation sensors, INS, or you call that GPS system. People are very comfortable with GPS. So there are two different philosophies altogether. Okay, something called dead reckonings, other one is called position fixing, basically. So that means there are very different ways of doing. Then there are a bunch of other sensors called magnetometer.
So if you could take a minute to give the difference, sir, like what is the difference between both of them? The GPS.
Dead reckoning and position fixing. Okay, position fixing is something like somebody is telling you where you are. In some sense, either you have to do a computation, but help is given to you, basically. Okay? So this is the way this GPS system operates. Is there is something called GPS receiver, and there are 24 satellites out there. Okay, theoretically you need 21, but 3 more are there in some sense. So at any point on the surface of Earth, at any point of time, you can actually see at least 4 satellites, at least 4 or more. Okay? So when these satellites are all equipped with something called atomic clock, basically, right? So they will exactly tell their position and from which the signal started time. Their position and time, the signal will come from like a packets of signal, basically, right? So when you receive that particular packet of signal, it will contain that particular satellite's position, all 3D position, and the time at which it got emitted. Atomic clock level, very accurate actually. So if you really talk about other one, there are 4 like that, then it's a simple Pythagoras theorem. You know, the distance between these 2 satellites is actually what? You can see all signals are light signals, right? So light speed c into time taken. So you have got a receiver time which is unknown to you, because your receiver is not really atomic clock. Remember, there is a clock but it's not atomic clock. Okay? So you have to estimate the time taken also in some sense. So essentially you assume that your own time is not known. So your own time is not known, but there is some T1 here, T2 here, T3 here, T4 here, something like that, right? So you take the distance between that, C into that C your current time T minus the T1 here, the delta T basically, right? T minus day1 delta T into C, that's the distance basically, right? So you know your position is also you don't know, x, y, z in T, right? You don't know, but that position is known to me. So what is the equation that tells you that okay, x minus x1 whole square plus y minus y1 whole square plus x minus z1 whole square is equal to C times delta T whole square. So like that 4 equations you put, and then the unknown positions are like your x, y, z here and the time. Okay, 4 unknowns, 4 equations you solve. Then there are a bunch of others, I mean that how much accurately you get, what there is some ionosphere effect, there are some differential GPS, all these things, complications start basically after that. But philosophy is, unless you have the satellites, unless the satellites emit the signal, you are blind as a receiver. Right? So that is where a lot of dependency comes when you have a GPS dependent thing, and that is one of the reasons why our Kargil war, there is some military code was not given to us and all that. So India thought about having its own Gagan system and all that. What you see as Navik system has a strategic impact of guiding our or helping our own strategic missiles. That was the whole idea.
okay.
The Navik system was a kind of byproduct for that actually. But anyway, that is GPS or the dead reckoning, the position fixing, we are fixing the position. Then there is something called dead reckoning. That means, okay, if you know your current position, like suppose I tell you close your eyes and go out of my room, you will be able to roughly do that because you know where is the door, what is there and which direction to go and things like that. So essentially, there are a bunch of sensors which operates on Newton's law. Newton's law, F equal to ma. So A equal to F by m essentially. So you figure it out how much force is acting on you, so and how much is your mass in some sense basically.
Then
the acceleration is known.
Yeah.
If you know the acceleration by now what is velocity? Integration of acceleration. What is position? Integration of velocity. So you do this double integration to get your position basically from that sensing. But remember, it has to be continuous sensing, and every time you integrate, there is a constant of integration. So that constant of integration, when you integrate one more time, you will get that constant of integration also gets integrated. That means if that is not really known accurately, okay, then you will have errors actually.
How do we determine this constant, sir?
That's a different story. I mean, I'll come to that problem.
Okay.
So that is why this. So there is something called calibration system. So you want to know this system very accurately, right? For example, when the launch vehicle starts going, they all calibrate it very, very precisely. So that means at that point of time when the launch vehicle takes off, there is no error actually. Okay, so that you need periodic fixing of that to get out of this bias. Otherwise, no matter, you can only minimize these constants. See, remember these constants by design they are made very close to zero. If they are very close to zero, error will not build up actually, right? So when no matter how much you try, whatever the precision level or something, whatever you do, there will be some amount of error basically, right? So in fact, the gyroscopes have that acceleration and rotation part of it. Now we are talking about translation. If they talk about rotation, there is something on gyroscope, almost similar. Newton's law equal to tau equal to I alpha basically. F equal to ma, tau equal to I alpha, like that. Gyroscope technology has improved quite a lot, so the errors are normally not much. But accelerometers normally have a lot of errors. Okay. In fact, all these small UAVs and all people will play around and all these engineering college and all that, they will talk about MEMS level sensors basically, right? The MEMS level sensors have typically more errors. Space grade sensors are much lesser error. So, but no matter what, there is an error, right? So you need periodic fixing. So what we really do in aerospace missions, critical missions, is actually a combination of both. That's a smart idea, right? You take a GPS INS fusion we call. Okay, you take the best part of it from the INS, inertial navigation data reckoning system and the integration based or whatever, and you talk about periodically you fix those errors basically. So remember now you are talking about, let's say you are going on a flight actually. I will give you a simple example, right? You are going on a flight and then passing through the let's say Hyderabad city, more or less Bangalore to Delhi, Hyderabad comes, and all flights normally go Hyderabad, almost over Hyderabad. Okay, so some pilots are a little bit informative. They will tell, okay, here is a Charminar, look at your left. That means you very clearly know that, okay, that is right now you are at Charminar. Because Charminar has become point of location basically, right? So whatever error you had before, it doesn't matter. So from there onwards, from there, whatever time is there, that is my location, because Charminar location is known to me. So that is how called periodically you fix it basically. So there are plus minus things again. I mean, for example, GPS system is not very frequently you cannot do it. The frequency is much lesser. INS system is frequency is very high. These are all technical details basically. So let's not go that.
Got it. Okay.
But after, coming back to your question, after you know the position, velocity, that's the navigation part. Then comes the guidance part. Okay, that means right now you know where you are, which direction you are going, right or wrong, whatever it is, and from there you have got a destination to go. Let's say you're again trying flying on an aircraft. You are at Hyderabad. The pilots normally don't do too much anyways. Okay, so think that is pilotless aircraft. Okay, now you know there is a destination called Delhi Terminal 3, some runway number so and so whatever is there available, right? So that means the aircraft autopilot computer knows where to go. That is what you call flight FMS, by the way, flight management system. Okay. So from there onwards, it recomputes and tell, okay, this is the path I have encoded basically, right? So right now I am here, but then I have to go here, and finally go to Delhi. That's what it happens normally. The pilots don't fly, computer fly basically. So that is where you talk, that's called guidance basically. So in fact, this Chandrayan mission and whatever, you know where the landing site. And whatever is that, whether you come or rightly or wrongly, whatever it is, keep on knowing your position periodically basically. That's why I call that intermittently they will open up a camera to know better. That's the intermittent position fixing, because from that onward there is a phase 2 or phase 3 will start. Okay, so otherwise there is no need actually. So when you come closer to the surface of moon, then you will open up some camera, then you kind of mesh the craters and all that, and you exactly know where you are. So all the errors that we accumulated so far is more or less gone, especially in the sense of altitude. Then from there onwards you guide it properly basically. That. So looking at the crater position, you know XY, and you figure it out to some sort of a altimeter, like laser altimeter or something there, and then the altitude also known. That means you know the position accurately. So from there onwards, that is why you call this so-called precision braking phase or something like rough braking, fine braking is so called like that way. So fine braking is not that the engine is suddenly operated fine. I mean that's the wrong terminology in my view. I normally don't call that as rough braking, fine braking. So what they talk is braking with rough navigation and braking with fine navigation. Okay, that's what we call it. So that way. That will be the correct terminology in my view basically. So our paper will talk in that language basically. But anyway, now coming back to that, is to figure it out what you should do to go there. Now you know where you are, okay, and then you know the destination where you want to go. So what should you do to go there? Which direction will fly? How much velocity will fly? Which angle will fly? So that part is called guidance basically. Not only you have to talk about your instantaneous velocity vector change, but you will talk about what all changes I will do throughout. How long, okay, right? So that I will go there. That part of the logic is called guidance. But remember that guidance has no meaning, that logic has no meaning unless you actually realize it. Right? Somewhere the vehicle is actually should realize. Suppose I am telling velocity V1 right now, velocity V2 right next basically. And these two are different. So I have to really break it in a proper direction to get it there. That is where the engine performance comes and all that. Actually. Which direction will fire, how much will fire, all sort of things. Right? That part we call is autopilot. So our control system. So essentially we talk about navigation followed by guidance followed by control. And essentially we call that NGC or loosely called GNC loop actually. So that is how it closes the entire thing basically.
Wow, this was like a very brief introduction into control systems altogether.